Okay, so here's the tone. AI for physics and complexity. Liew from NTU is my fellow co-host here. We are partially pretending to know what we're doing, at least that's me. It's a great pleasure and excitement that I welcome you to the AI for Physics Complexity. Today we gather as a community of dedicated physicists to explore transformative potential in artificial intelligence in understanding the complexities of the physical world. As we gather here, we stand in a pivotal moment in history. The rapid advancement of AI holds unprecedented promise for revolutionizing our approach to scientific inquiry and discovery. From unraveling the mysteries of the cosmos to deciphering the complexities of biological systems, AI offers us a powerful lens through which to explore the fundamental principles that govern our universe. Over the course of the workshop, we will engage in thought-provoking discussions, share insights from our diverse areas of expertise, and collaborate on defining the key challenges that would drive progress in AI for physics and complexity science. Together, we will explore topics ranging from the development of AI algorithms, for analyzing complex data, to integrating of AI techniques with theoretical models in physics and beyond. But this workshop is not just about identifying challenges. It's also about charting a course for action. By identifying the grand challenges of AI for physics and complexity science, we lay the groundwork for future research initiatives, collaborations, and investments that will push the boundaries of what is possible and lead to transformative breakthroughs. All of that was written by ChatGPT. You can tell because the images were also, yeah, somebody guessed it. Because you guessed that the image, the text that I put, I gave it to Midjourney to generate the images. Just copy and paste. What does this show us, right? That you might be able to tell that the images are wrong if you look really closely. And I think that's the very important part of this workshop. The details are what is important for us, especially in complexity. So let's actually go to some real content. Back in 2019, a few of us wrote a proposal that's called cheekily AI for Science and Science for AI. Right? It's 2019, and there's some ambitions in there that we'd like to share with you. The feedback we got about the proposal back then was it was too ambitious, circa 2020. So we'll see whether 2024 is ambitious enough. And this is a central question. To whom does explainable AI explain? Right? We talk about explainable AI all the time, but who is it explaining to? So let's start from scientific principles because we like textbooks. That's why we're here, and that's what I'm here. The word principles often appears in and on our textbooks. It would appear that principles somehow explain our world in some fundamental way. In this cartoon, proposition 1 can be somehow explained by proposition 2, and can be in turn explained by proposition 3, and so on. If you're a physicist, you probably understand the turtles, right? Principles are in some sense the terminal explanations, which is why they're called first principles. So defining principles as terminal explanations suggests that they're somehow axiomatic, right? But for practical explanations, you also depend on the target audience. For example, to a physicist, your chair that you're sitting on, most of you are, holds you up because the chair is made of atoms. The atoms don't collapse because their electrons exhibit mutual degeneracy pressure. This pressure arises because electrons are fermions, and two fermions cannot occupy the same quantum state. You might recall this as the Pauli exclusion principle, the key postulate in quantum mechanics. And although this principle has not been violated so far in our observations, I don't think we can fundamentally explain why this principle should logically follow. It becomes like an axiom for us. But this chain of explanation is unlikely to satisfy a 3-year-old, right? Whose experience and priors are very different from yours. So what is explainable to the 3-year-old is different from what is explainable to a physicist or any other training that you have. So it's inevitable that explainability is anchored to your prior knowledge. In the natural sciences, this means anchoring to the core principles in classical mechanics, physical physics, and so on and so forth. Starting from a scientific principle, we can derive a broader set of mathematical equations that are useful for understanding our physical world. Composing multiple parent principles can lead to emergent disciplines, such as condensed matter physics, biophysics, and all the other interesting many-body stuff that we see. However, these emergent principles often have theories that need to be present in their although they have in their present parent disciplines, which makes reductionism and extrapolation from the data imperfect. So for example, condensed matter physics uses emergent models to describe how many bodies interact and behave dramatically, so on and so forth. But it's hard to go backwards. It's hard to reduce back in some of these cases. Or, as Philip Anderson would say, more is different. So an AI companion, which is the kind of stuff that we all use right now, in some form or another, can, we hope, help us co-discover emergent principles that should be interpretable to us and explainable to us. Practically speaking, this means that the AI companion learns from a corpus of observable data and identifies signatures of potential principles that are interpretable by conservation, symmetries, invariants, things that are recognizable to us. And these signatures are then explainable when we anchor them to known or as yet unknown scientific principles. All these are slides from 2019. If it's incoherent, it's because I've not practiced it for 5 years. But this is what our vision was. So nature is unimaginably creative and complex, yet her expressiveness is expected from us, from a relatively small set of fundamental laws and mechanisms uncovered or awaiting discovery. When will AI discover novel first principles? It's no longer a question of if, that are beyond any single human's intellectual capacity. And when it does it, or it's they, I'm not sure what's the right pronoun here, will we be able to understand this discovery? Okay, so that sets the big ambition that we set out back then. I would like to see if things have changed a little bit more now that we have ChatGPT and the journey. And now for some actual science, which means the speakers will have to get ready to talk. We're a little bit ahead, so whether the speakers can set up. This is the schedule. We're going to start off with Dario, who will tell us a little bit about many-body physics, Shen about computational materials, Kishor about quantum machine learning, critical phenomena, Feng, Timothy Liew on quantum optics, complexity science from Liew, and me. I mean, I inserted myself because there was if you remember from the actual email sent to you, Marvin was supposed to have 30 minutes, but then he's going to consolidate as a sharing at a different time. So I've inserted myself. If you boo me off the stage, I'm happy to stay quiet so you guys can talk more later. Okay. But with that, I'm going to hand the microphone over to Dario. Okay. Which means
thank you. Hi everyone, I'm Dario from SCTV. Thanks, Dario, and Duane. Can you hear me? Okay. So what I'm asked to do is to give a rough idea of what we are doing in my group and some people are here in Singapore and around the world, and also maybe propose some challenges and some big questions or some difficulties that can inspire discussions later on. So that's what I'm trying to do now. And this is people in my group. The people in blue and the collaborator on the right are people who are more actively working with me on these issues. Okay, so two main things we pursue in my group currently. One is quantum-inspired machine learning, and the other one is neural network quantum states. What I mean by this is here. So by quantum-inspired, we mean techniques that have been developed in quantum many-body physics, mainly, to describe complex quantum systems. And we realized actually they have a good expressive power, they have nice learning properties. So we try to translate them to other domains, okay, and see how they work. The other one, neural network quantum states, is using neural network as an ansatz. If all physicists, most of us are physicists here, you know, variational principle, you can use any function. Now this function actually could be represented by a neural network, and then try to see how far you can go with that. Okay, let me give you a little bit more details. This is the idea of the tensor networks, not familiar with that. Let's say you have a a wave function or a general probability distribution also, it's fine. And it's given by these coefficients. And usually there is an exponentially large number of them. If a system has L sites, you will have 2 to the N, for example, for speed house. But these coefficients can always be written as a product of this of tensors. And this can be exact, okay? And in the case, this tensor would be extremely big. But it turns out that in many cases, using small tensors, you have enough expressive power that you can describe many interesting states. And this is a graphical representation which I put here. This is what a wave function looks like when you think about tensors, and these are three-leg tensors that multiply together when two line joints means they are multiplied together. And the idea of using these tools to do classical machine learning tasks, I think a groundbreaking paper was by Studemeyer and Schwab in 2016, and then followed by other people, and we also follow suit, and we did some different things like sequence-to-sequence learning. So we expanded from classification to sequence, and here the idea kind of graphically represented here is you turn some data into a simple tensor network, and then you learn some operators that get as an input this tensor network, output the tensor network, and then you convert this tensor network into data that you need. And we've used it to do deterministic cellular automata evolution. This is an example. This is the predicted evolution of a fairly complex dynamics. As you can see, it's chaotic rule in the cellular automata. But actually, we know, we found that you can describe this cellular automata rule exactly with these tensor networks. So the idea of using these tensor networks compared to other neural networks, and you know that you have some exact solutions, you have some guarantees which are quite robust, and you also have beautiful learning properties. And we tried it in different activities, even to do quantum process tomography. Let's say you have a complex quantum system, and you try to do some operations on it, and then you look at the result at the end. And basically your inputs are unitary operation, for example, that you do on the system, and output is the final density matrix. This structure that takes these inputs and returns this output can be written as a tensor network, exactly. And it also gives a lot of insights into what you can extract. So the interpretability power of these quantum-inspired machine learning tools is actually pretty good. And so we used it also with some experiment and to predict how this will behave, even in presence of noise, which we have no control upon. The other path that we pursue in our group is what I mentioned, neural network quantum states. This was first developed in 2017, not many years ago, by Giuseppe Carlea and Matthias Troyer, and he boomed afterwards. There is a lot of interesting progress and challenges. The idea is quite simple. You put in some configuration. For example, you have a spin chain. You have a configuration of ups and downs, so zeros and ones, basically. And the output is going to be a complex number, which can be psi, or some case the log of psi, because it's convenient for some calculations. So the idea is quite simple. What you do here, instead of doing supervised learning, you can do unsupervised learning. You just need to optimize a loss function, which is, for example, if you're interested in the ground state, you will reduce the energy of the system. Similar, really like variational solutions. And you can do similar things also for time evolution. The thing is that these problems here with the energy is turning to computing an expectation value of a probability distribution that's given by your neural network and some functions that you can easily evaluate and in general efficiently. Of course, over the years, this is some review, but of course, times passed, there are many more results. At the beginning, they used simple restricted Boston machines, then they evolved, and you use feedforward neural network, convolution neural networks, and finally, of course, transformers. Okay, okay, so there are some challenges still. And I didn't want to talk too much about what we're doing. I just want to give an idea of some of this research and action. And then I use the last minutes to talk about maybe some challenges. Okay. And this is the slide that conveys some of the challenges that we face, and I think maybe are common to some of other domains. Of course, we want scale, speed, precision, flexibility, interpretability, which are also related to some of the things that Duane mentioned just now. Let me try to spend maybe a few seconds on each of these points. Can we move easily across scales? For example, let's say I find the ground state, I have a neural network that describes my ground state very precisely for 100 speeds, okay? What can I use from it if I want to describe the same system but for 500 speeds, okay? Do I have to retrieve a network completely, or how much information can I transfer from this to the other? We did some works in this direction, but there is still a lot more that needs to be done, at least in our field for this. And with tensor networks, this is, especially if translation is valid, this is straightforward. But for neural network, is a little bit less. Now, can we move across levels of accuracy? Let's say I want to know some properties at 10 digits precisions, but then later I need to actually only need 5 digit precisions. So I may need a much smaller neural network to do that. Much less parameters, much less training data. But what can I use of the previous one to have to retrain everything again and for different accuracy levels? And I know this is a problem that in many fields appears, and you know, there are some ideas out there. So this, do we need such a massive sampling? Okay. Is it really necessary, or we're missing something? There are various techniques, of course, covariate and many other. You putting more physics, symmetries in your system. Okay, I mean, structuring architecture in a way that less samples can be used, and this can increasingly speed up your system. But sometimes, you know, we're describing highly complex wave functions with huge changes. So maybe we really need a significant sampling. And then is this scalable? Is there a huge bottleneck there, or can we really go forward? So this is a big question. And you know, we in the history of AI or machine learning in general, you have seen that one of the key that developed the system was really getting more computational power. Okay, so basically, a lot of things that were successful in the 2010s could have been done before, but there was not enough computational power. Of course, there was also algorithmic developments and so on, but computational power was really necessary. But is it really a necessity, or is it an overkill? If we put in more physics in these neural networks, can we speed up things? And are there other architectures that can be better functioning? Okay. So this is some of the challenges, things that I thought there could be for some good discussions today, and I'm sure many of you have other, maybe even better ideas. Okay, that's it.
Yeah. Sorry, because we're running like fast. So the questions we have to save for the coffee break. If you can write it down a little bit. The next person. This is like Blitz talk. The next person that will be presenting is Dr. Shen. Tell us about computational materials physics.
Thank you for introduction and the invitation. Yeah, I want to share my own thoughts as well as my experience and the lesson. Because previously I want to use AI to generate some about the opportunity challenges AI computational material physics, but I gave up since I know the organizer invite me here to want me share my own experience and the details, right, instead of the general discussion from the ChatGPT. So I promise everything I prepared today, right, is made by myself without any help from ChatGPT. All right, now let's move on. Okay, I'm Shen from Department of Mechanical Engineering. So I want to share some of my own thoughts about challenges and opportunities of AR in computational materials physics. Yeah, here, this slide just shows right the traditional computational material physics methods and the challenges. So, what is the traditional computational material physics do? Right? Yes, we study from the material structure. It can be crystal, metals, alloys, right, like polymers or composites. And then we'll extract the parameters such as elemental parameters, structural parameters, or experimental parameters into the model or computational models, such as density functional theory, molecular dynamics, and so on. Then we'll do the calculation by solving equations, right? After that, we obtain the physical properties, right, such as structural relaxation, band structures, the thermodynamics property, and so on. So this is a traditional computational approach. Now, however, right, just two examples, right? For the governing equation in DFT calculation is a quotient equation, as can be seen, right? We need to obtain the potentials as quite complicated many-body interaction potentials. And also we need to solve by the partial differential equation. That is very complicated. So we face a lot of challenges in like DFT and molecular dynamics simulations. Now the motivation of the AR as well, right, into the computational material physics is very simple and straightforward. Just right to predict the properties directly from the material structure without solving any equations. Because we know our AI has very powerful ability, right, to handle the underlying relationship between inputs and outputs. So that's why we believe, right, the machine learning also can find a relationship between the structure and its properties without solving any equations. So this is the very early motivation, right, in AR in the computational material physics field. Yeah, so that is the in the early stage, right? The motivation is very simple. Just using the AI. Here is a structure, right? We study from the structure, generate the features of descriptors, and input the feature descriptor into the machine learning algorithms and predict the properties. All right. Here I want to using my own works, right, as examples to demonstrate how, right, to predict the property directly from structure and what a challenge or lessons I learned from this research works. So the first work is like we predict, we know like DFT is a problem in predict the band gap, and the GW can give very accurate band gap, but it's very time consuming. So that's why, right, I want to use AI to predict the GW band gap. All right. But we have the challenge. The challenge is compared to the DFT, accuracy, you find all the error of the machine learning model. Usually the 2 or 3 order of magnitude higher than DFT level. Yeah. And we'll also do some calculation, right, to prediction using the AI to predict, for example, the flat band of 3-dimensional alloys, as well as the voltage, right, you predict the voltage of the materials for lithium-ion batteries applications. And for such kind of complexity systems, we notice the accuracy is a big issue. Now, the reason for such kind of issue is no matter, right, we improve the domain knowledge or integrate domain knowledge into the descriptor, feature engineering, optimize the machine learning algorithm, we still cannot get, a satisfied accuracy of the prediction. Now we notice the reason actually is the data set, limit of the data set. Yeah, for example, the 2D semiconductor, we only have around 100, data set. For the 3D alloy flat band prediction or, material voltage prediction, just thousands data set. So it is not enough to train the AI model. So the issue, right, is the data set. Now it boosts the next stage of the AR in computational science. It is named, right, material data generation. So we want to generate as many as possible material data set. So there are two ways to generate a large amount of material data, or one method is called high throughput DFT calculations. The other method is generative AI model. Yeah. Now, for example, we develop a 2D material database, which includes around 10 key 2D material structures. And another famous, materials database is a material project. It includes around 150 key 3D material structures. Yeah. And then, a lot of 2D material and 3D material database have been developed over the past few, years. Yeah. Then with the, the high throughput database, like this example, right? Google DeepMind team, right, developed a very famous model, like Genome, which generated around 2 million new 2D materials. Yeah, so that is according to the record, the human experimentation material is only 20 key, but this model can generate 2 million new 2D materials. Yeah. So although the high throughput calculation, the generative AI model can generate a large number of materials, new materials, but there's still some challenges, right? The first challenge is the data accuracy. Because of the nature of the high throughput calculation, we sacrifice accuracy. Usually we use a PBE level. Okay, and the machine learning model, the prediction accuracy cannot be higher than the accuracy of the training data set. So that's why the accuracy, all right, of the generative AI models usually is lower, even lower. So this is the first challenge. Another challenge is usability. Right? For example, this Song, right, and his collaborator predict around 250K 2D materials. However, only 92 confirmed IDFT calculations. I'll also plot some, of the predict structures as can be seen. Right, this is MNPD, the group space is P6, right, MMC. As can be seen, the structure looks very weird. Yeah, so it's kind of rubbish. Yeah. And how about the DeepMind group materials? Yeah, so I also check, right, the distribution of the data set. This is the binary compounds. The left-hand side is a material project according to the DFT calculations or experiment. As can be seen, the binary materials usually, right, the distribution is like AB or AB2 or AB3, and mostly AB, AB2, AB3. However, the DeepMind genome predict the material distribution. Can be seen some weird chemical formula, like as hydrogen, right, boron 35, AB 35. There are a lot of material has very weird chemical formula. Yeah, so that's kind of a problem of the usability, and also around more than 60% of the prediction in the 2 million materials are intermetallics. Yeah. Another problem is kind of called interpretability and credibility, right? Because the generative model, the materials generated by the generative models is, as can be seen, right, there's no any physical explanation, right? So that's why we need to consider the interpretability and the credibility. It's not currently the model is just a black box. Yeah. Last challenge, I think, is the generalization and extrapolation capability. So generalization is kind of a distribution of the generated samples should be similar, right, to the distribution of the training data set. And also the sample distribution, as can be seen, right, generated by the genome is not similar to the distribution of the training data set. So that is another issue, which is called like extrapolation capability. I summarize a few, potential solution opportunities to address those challenges. The first one, right, we need a high fidelity calculations, such as the hybrid functional calculations, the meta PV calculations. Yeah, so far we also we're doing the hybrid functional calculations for our 2D materials, but it's very time consuming. Yeah. Another is called physics constraint. Physics constraint, like we can embedding the domain knowledge into the model. For example, you can use the domain knowledge to do the data cleaning. You can use the domain knowledge to generate the features, descriptors. You also can integrate the physics into the AR models, right? So that's called physical informed or physical integrated AR models. Yeah, last one is kind of uncertainty quantification. So what is uncertainty quantification? Usually, right, how to evaluate the performance of the AR model. Most AR model will be used evaluate using like the mean absolute error, right? Yeah, a root mean square error or the I-square, right, to evaluate the accuracy of the model. However, we also need, right, some uncertainty quantification method to evaluate how reliable of this model or how the prediction confidence of the AR model. Yeah, such as ensemble and the delta methods. Okay, so that is the opportunities in this direction for the generative AR models. Yeah, as mentioned, the interpretability or the explainability is very important for AI model, especially in the field of physics, right, domain. Okay, so now how to make a model explainable or interpretable? So far, right, two advances in this field. One is called to develop a deep learning Hamiltonian, as well as a deep learning interatomic potentials. Right. As mentioned, firstly, our idea and motivation is directly from the structure to the properties. However, as can be seen, right, there's no any physical, governing equation behind this prediction. So that's why currently in this domain of community, right, this research is trying to develop the deep learning Hamiltonian of potentials instead of directly predict the properties. So that's why we can start from the structure to the Hamiltonian, from structure to the force field. Right. After that, we'll solve the equation, the physical equations to obtain the physical properties. So that's why the models now become the explainable, yeah, or kind of gray box or white box. Now here's two examples, right? For example, using the deep learning Hamiltonian, they can predict the trace by graphing layers, right? Like the maximum number is 1.08 degree, and the total number is more than 11 key. And also can do the molecular dynamic simulation based on the deep learning potentials. So the size of the number of atoms is 8 million atoms, and the time period is more than 200 picoseconds. So it's critical, right? Yeah. Now, however, we still have some challenges. The first challenge is data accuracy, okay, and the diversity. Yeah, and I want to highlight the challenge is invariances and equivariance. Yeah, so any crystal has the symmetry, right? During the rotation, translation, or inversion, you be sure, right, the structure is still the same structure. That is called invariance. But because the high order calculation such as tensor product, yeah, so it's very time consuming. Then the opportunity of potential solution is to make lightweight AR models, right? And the last one I want to highlight is, again, right, we need a high fidelity calculations such as MATPB or active learning. Active learning is kind of integration of AR into the DFT of computational method. So let me quickly, this is a summary of my talk by evolution of AR in the field of computational material physics. The first stage, right, just develop a structure property relationship using the traditional machine learning. The main task is develop the feature engineering. And then the second stage is develop a material database, right? Increase the number of the data set, yeah, including the high supercalculation or deep learning, advanced deep learning models. The third stage is develop of the Hamiltonian or the interatomic potentials of force field to make the model more explainable. And I think the next stage, right, is to generate a high quality data as well as the data fair. Right? That is the data standard to make the data findable, right, available, right, reusable, and so on. Yeah. And the last one is called advanced machine learning techniques such as the active learning, as well as collaboration within the community. Thank you. And all my job.
Thank you, Sydney. It's, I think, very unfair to ask people to summarize a whole body of work in 10 minutes. Because this is AI for physics, and physics has a long and storied history. So while I stall so that I can get Kishor's slides up. PDF, perfect. Love this man. Okay, so next speaker, I was told Kishor single-handedly started the quantum machine learning club. Machine learning or AI in CQT, something like that. I don't know. Maybe you can tell us more about this. So anyways, this is Kishor, and 10 minutes, please. Thank you.
Yeah, thanks a lot. So people talked about, AI for quantum. I will talk about how quantum and AI interact both ways. Right? Like AI can do something for quantum, quantum can do something for AI. And actually I had a slide, 1 hour slide, this, so, so condensing it to 10 minutes, right? And still I would say it's very biased. So, yeah. So, we all know we are in this era of noisy quantum devices. There are so many claims out there that we have done something unprecedented, though that's debatable, but it's interesting. But you see that there is this, my friend Marco, there is this review paper, challenges and opportunities in quantum machine learning. So that solves the purpose. Let's say you can just go and read this, right? And see all this. But, and there are other, works also, for example, at some point we covered in this review paper with, I think, Alan's Buzik was mentioned, with him. We discussed about quantum, let's say, current quantum devices. Then there is this old reference by, not very old, by Patrick and CQT. And Anurag, who was, from CQT, not Harvard, a survey by him, assistant professor there, survey on complexity of learning. So there's a lot of interesting work, but then there's a lot of challenges. Yeah. So quantum and AI can interact in very interesting way. You can have algorithm and you can have data, and depending on the sets, classical or quantum. Many people have seen this, right? And so you can have classical quantum. So wherever there is any quantum part, you call that quantum machine. And you can see that quantum for AI or AI for quantum, all that of quantum for quantum, everything is quantum machine learning that we can do. So you can talk about QML approaches in 3 different ways. There can be fault tolerant quantum machine learning algorithms, those for the far-term quantum computers. Risky QML algorithms, those for near-term quantum algorithms, quantum computers. And the third one based quantum learning theory, more you can say proving guarantees and separations and statistical complexity theory, machine learning perspective, statistical learning theory perspective. And for all of them, you can see some references where but there are many challenges. And whenever you see a quantum machine learning paper, you have to read the fine print. So this is why Scott Aronson and there are many tools which are used inside many of these machine learning algorithms, and you have to see whether what are the assumptions there. And sometimes these assumptions can lead to any claim of advantage will not so anyway. So for example, there was this major paper which was dequantized by a teenager, like Ewing Town, and she has done many interesting work in this direction. So you can see there are many interesting challenges. And over time, very fast the community has evolved, and Srinivasan and others basically wrote this interesting paper. We're using ideas from crypto. Basically, they gave a rigorous and robust quantum speed that also machine. So there are many challenges, but let's say if you manage to do something interesting, the dividends are also high. So AI can help quantum, but here quantum is helping AI. Then there is a nice paper by Robert Wang, Sit and Chen and others about exponential separation Similarly, one can talk about topological data analysis and a lot of interesting works going around and so on. And yeah, there was this nice paper by Seth Lloyd, which kind of talks about the limitations of quantum algorithm for topological data analysis, which is important for AI. So it's very important to think about what are the problems for which quantum can genuinely help. And I will talk about some places where AI can help quantum. And you see it's QML is a very fertile ground where AI and quantum very nicely interact with each other. But there are a lot of subtleties, a lot of nuances, and that's why that brings the challenges and that brings the opportunities. So you can see, this was 1 hour talk, so I cannot explain all of this in detail. But you see there are many important problems for which you can get separation, advantage, and quantum. Similarly, there was this nice work by Liew, Jane, and others, where how few data points could be used to provide some inference tasks. Similarly, there was a paper by Matthias Faro, Patrick Coles, and so on, where they say how generalization is much more easier in the quantum discuss. So few data points you can generalize. Then there is notion of quantum neural networks, similar to the notion of classical neural network. And there are many roadblocks, some of the roadblocks we also at some time talked about in different papers. And there are problems related to trainability, finding better circuits and so on. And one can ask how to characterize the power of these parameterized quantum circuits. Can we avoid barren black hole and barren optimization? Can we improve training of these variational algorithms? Can we design better classes of these algorithms? We know some partial answer to this, but it's very much unexplored territory. This can go in challenges. Finally, this is the holy grail of this, let's say, current term quantum computing. This is the last slide of this I will stop. One can ask, first of all, can ML help us find this task? And the second question is, let's say, can you find a task for which, let's say, it's easy to, implement that task on a quantum computer, difficult to implement that task on a classical computer. And once the quantum computer has implemented the task, the solution is easy to verify. So feasibility, verifiability, and soundness, all these three are missing for any problem. We forget it for them. And let's say if you find it for ML, the evidence will be verified. So this will be again which can go in challenges and opportunities with these applications. That's it.
Thank you, Kishor. Wow, 1 hour into 8 minutes. That's like magic. Ling, yes, I have your slides. He's going to talk to us about critical phenomena.
Hi, morning everyone. Thanks Duane, Liew, and RIF for hosting this. So I'll talk a little bit about critical phenomena. It's a little bit probably higher level given the time constraints. So I know it falls within the study of complex systems, but everyone has a different conception of what complex system is, and what you need to study. But I guess more or less most people, physicists, agree that critical phenomena is the epitome of one of the most important things to study in complex systems, at least by physicists. So I organized the flow of my talk into, of course, align with NRF's plan into data, compute, and science, and how AI and advancement in computer science engineering help us or help the community in the workflows. So other works will be presented down here is with my colleagues in HPC as well as my colleagues in NUS physics as well. Just show, so first about data. So the challenge in data is real-world complex systems are usually have incomplete data, right? So due to the limitation of data collection, errors and stuff, so that's always the case when we deal with real-world data. So the opportunity is, of course, is you can use AI to augment the data or enrich the data. So there are a lot of work people have been doing. Not all the work has been highlighted, but I just probably highlight two relevant works that I've been involved in. So the first is about reconstructing. It's a recent work that gets published. So it's reconstructing the evolution history of network systems using AI. So here we use graph neural networks. We're trying to see how we can reconstruct the evolution. So a lot of networks are temporal networks, but you don't really observe the temporal history, how it came about. And the temporal history is the dynamics, as we know in physics, that the dynamics of the system, how it emerges, it tells a lot about the underlying science rather than the static information of the network itself. So that's very important. So AI can help us to recover or give more details on the temporal information of certain data sets, and that gives us more data to study the science behind it. So another work is about urban systems. So we have been studying urban systems. So our team at HPC has spent a lot of effort in urban systems, and recently we started to use AI in our workflows. So in this particular case, we are trying to use generative AI, in this case, generative adversarial networks, to augment the data, because a lot of data we collected for Singapore transportation is not complete. Actually, it's very incomplete. So there's no way you can make a very complete data. So that's why we use GANs to make the data set more rich, more complete, so it can help us do better science or analysis. So next I go to compute, how advanced compute has helped us. So the challenge, of course, is real-world complex systems analysis, because complex systems usually by definition is large many-body interactions, but nonlinear interactions. So it's a lot of compute-intensive process if you only analyze the real data. But of course, luckily we have GPU accelerations. So I just give one example of how we have been leveraging it. So this one work, so my colleague Jeremy and I have been involved in this Katos. It's a new center on the Asst to study the social media. So we have been looking into the social media, the local social media in Twitter, now X and TikTok. So both things are really gigantic, even just for Singapore. So if you look at Singapore, X account has millions of edges for local users, and TikTok in Singapore has billion edges. So that's really gigantic, and both are changing with time. So if you want to do real network analysis on those, it's really, really compute intensive, not just data intensive. And a lot of network metrics like community detection, influencer detection, misinformation detection, they have high computational complexity. And they are intrinsically higher than the spatial data because there's a lack of spatial symmetry in those data. So what we have been doing is we have been leveraging on the CUDA library called MVGraph developed by NVIDIA. So we use the GPUs to accelerate the computations for some of the analysis. It drastically shortens the computational time from days to minutes, which is really amazing. And what is more amazing is that when we develop in the code, with the help of GPT, so we don't have to learn all the nitty-gritty of the libraries, how to do it. We just ask ChatGPT to do it for us, then we just need to fine-tune the code. So it really drastically shortens the whole analysis time and development time for the whole process. So that's how compute has been really helping us tremendously. But lastly, of course, we are here for the science, right? That's the most important. So the challenge in complexity science, or rather I would call it the science of complex systems. So it's one of the main ones is why real complex systems are adaptive and efficient. Why they are. It's still ongoing research and it's still ongoing mystery. So of course, a lot of such studies anchored upon the notion of critical phenomenon, as in the sense that these real complex systems we observe in nature and social science or society, they are actually similarly operating at a critical point. Let me give you a more concrete example. This is a Nature Physics paper published just last year. It's looking at a complex system of fishes. It's not people, not physics. It's animals. So you look at a show of fishes, a lot of fishes. So how they move around, how they behave, how they then they use, of course, they also use machine learning. Like in this sense, they use long short-term memory, which is RNN network architecture, to help them to distill some of the parameter changes in the networks. And what they found is, it looks like when they are empirically calibrated theoretical model. So it looks like at the critical point, the information propagates most efficiently across the whole population. Like so the fish can coordinate among themselves to react to its external either predators or food. So this is a very intriguing notion, has been lingering in complex systems for decades. So as you can see, the last sentence says our results suggest that criticality may be the possible principle of distributed information processing in large animal collectives. So essentially what it says that if you understand why complex systems in the real world are adaptive and efficient, we need to anchor our study on critical phenomena. And so the next, naturally, the next flow of thought is how to anchor this adaptivity, efficiency, and criticality, right? So you can further drill it down to information processing. So because adaptivity and efficiency means information propagates just the right amount and very fast across the complex system, which is a collective. So of course, then there's a lot of studies on complex systems. People study about the biological brain, information processing. So this is a recent review paper in Cell. So it's talking about how critical is brain criticality. So somehow among the neuroscience community, it has been somewhat a recognized fact, empirically at least, that our brain, human brain, a healthy one, operates at a critical point between order and chaos. So of course, it's still ongoing research to understand deeper why is it so and how is it good. There are some research, theoretical aspect and empirical aspect to just advance this, but there are still limitations. Let me just talk about it a bit. So there are some physicists, there's a lot of physicists working in this area as well, although we are not neuroscientists, but we have our special thing to offer, which is critical phenomena, right? We know the mathematics, physics behind, so we can help them to understand this. So, so then the problem with a lot of those systems to unlock the science of complexity is that the biological brain is not that easy to experiment and examine, right? Unlike artificial brain. So artificial brain, you can do whatever experimentation, controls, and examination at any microscopic details you want. And now artificial intelligence has achieved human brain performance. So it's actually a very good subject for examination to unlock the new science. So it's here we just like to talk about a little bit of some of our relevant work with some of our collaborators here. So a few years back, we started looking into if the state-of-art artificial intelligence models trained on real-world benchmark data set, whether they do also exhibit this edge of chaos phenomenon, and if it is, whether we can understand it better. It turns out, yes, we can. Actually, they do. So we tested on various image recognition networks, CNNs, ResNet, DenseNet, and all without fail. When those machines are optimal performance, they do operate at the edge of chaos. And then through examining the dynamics within the neural networks and manipulating them, we actually uncover new science, which is this phase diagram here is about a dimension against the asymptotic Jacobian norm. So essentially, generically, we don't say all, but most generically, then dynamical systems will fall into these three regions with a shrinking middle region as the dimension goes higher. So we then further leverage on this theoretical finding, and then we actually apply it to neural network training processes. We realize that if you really constrain the training to the model to explore the ways configurations at the edge of chaos, actually you achieve better performance than otherwise. So we set a principal way to set the hyperparameters of the trainings. Now, of course, we also applied this into one of the competitions, in one of the leading AI competitions in NeurIPS 2020, and we got top 10 positions just using this theoretical intuition alone. So then, yeah, so further, of course, as I mentioned, AI as a subject can even help us to explore further on how criticality exists and arises from neural networks. So we did something about LSTM, and we found that a striking similarity with our biological brain as well. So yeah, so this is my last slide. So again, data, compute, and science. So AI augmentation, data augmentation, it can really help us to get more useful data for research into complex systems, and GPU acceleration can really get us way faster compute that will actually quite, Then the third one is, rather than just study AI, using AI for us, but actually we can study AI as a subject for complex systems and uncover new science within complex systems. So that's what I'm trying to say. The science of complex systems is a lot, and I believe that a lot of us also believe in the community that critical phenomena is the key to unlock this new science. And this will in turn explain some of the very, very important ideas underlying complex systems, which is why systems are when adaptive efficient, or what's the balance between control and self-organization. Most, of course, very importantly, how do you explain the complexity? So yeah, then of course, in terms of real-world applications, we thought once you unlock the science, then you translate to this higher level explanations, then maybe you can apply to healthy online social network regulation, better urban planning, or even tools for biomedical neuroscience research. And last but not least, it may help us to pave way to understand AI better, to explain AI, explainable AI. Thanks.
Thank you. Wow. My brain is a little bit overloaded. We went from very small scales to now very big scales, and then we're going to intermediate again with Tim. Let me try to load this. Okay. All right, Tim, the floor is yours.
Thanks very much for the introduction and for arranging this. So I'm afraid my topic is a bit more niche. It's not going to be so general. I'm not sure what are the grand challenges here, but I want to say about the field where I'm working, which is this field of semiconductor microcavities. These are the structure here illustrated on the left. So these are made of multiple layers of semiconductor. Alternating layers of refractive index on the top and the bottom serve to create highly reflective mirrors. The purpose being to confine light so that it interacts with the lowest lying excitations in another thin layer of semiconductor, which we call the quantum bubble. These lowest lying excitations are essentially bound pairs of positive and negative charges. There's electrons and holes, which we call excitons. The excitons act as artificial atoms. As atoms can couple to light, so can the excitons. And when that happens, we get rise to a new kind of hybrid molecule from this artificial atom and photon of light, which we call exciton polariton. And why we like exciton polaritons is because in the same way that molecules derive new unique properties, even though they're composed of different atoms, the exciton polariton can have different properties, even though it's composed of exciton and photon. We can think of it as the condensed matter physics system with coherence, or we can think of it as the photonic system with a decent amount of nonlinearity. And so for 20 years, people studied these planar microcavities, but the growth techniques and fabrication techniques have improved now. And so now it's possible to vary in space, in the plane of the microcavity, what is the thickness of the cavity layer. And this will create specific traps for the polartons. Do I have a pointer on? No, okay, never mind.
You can move the mouse on the side.
Oh, no, it's touchpad. Okay, so this was validated. Okay, never mind. Okay, so yes, so these are the kind of regions where the cavity layer is thicker. These will act as kind of nodes where the polartons are confined. And so when I speak of nodes, we're trying to think how we can use this system to form a physical implementation of some neural network. So indeed, we have nonlinearity because the exons, that is these artificial atoms, they can interact with each other. They give rise to an effective Kerr-type nonlinearity. However, the problem we have is that the mirrors are never perfect, and so the light is always escaping from the system, meaning the polariton, it continuously dissipates its energy. So you might be able to have the polariton hop from one of these nodes to the next, maybe the next, but you cannot have it hop indefinitely. So we cannot have a continuous cascade. And this is maybe bad because typically when we think of neural network, I think we tend to think of many neurons arranged in many layers, and we want the information to go from one layer to the next and cascade forward. So we can't really do this here because we're all the time losing the polaritons. Fortunately, though, there are a few other architectures of neural network, and the one that we've been studying is known as reservoir neural network. So this replaces this paradigm of having many layers with having just a single layer, which we call reservoir, and reservoir is composed of many nodes that are randomly connected. So we aren't even going to bother controlling the strength of couplings between these nodes. We just have them in some random lattice or random graph. And we'll also allow the coupling to go both ways. So this becomes a recurrent neural network, which is also maybe better for the photonic system. After all, with photonics, you tend to have things like time reversal symmetry. So the signal is not always going in one way, as you might have in a feed-forward neural network. It may be going forward and backward. So it seems to me the recurrent neural network might be more appropriate, at least for this system. So we have some input, which we can just have as some optical field that excites the different microcavities or nodes in our network. And we aren't even going to bother to control the weights at which that input is sent into the system. So we'll have a rather easy system or relatively easy system to fabricate because we won't have to worry about so many of the tunings of the weights. Of course, everyone knows when you're making the feed-forward or deep learning networks, it's quite critical to choose the weights to get the desired function. In the end, we can measure the average intensities of the different cavities, and then to get some functionality, we will have one trained layer, that is the final layer, where we linearly superimpose those different measured occupation intensities, occupation numbers, with controlled weights. So we proposed this a few years ago, and people did the experiment. We applied it to the most basic task in machine learning or physics of neural networks, that is the recognition of handwritten digits. And it turned out that the polariton system did quite well compared to the other physical realizations of reservoir computers or reservoir processors at the time. This success rate, though, is certainly not the best that a neural network can achieve. Definitely, the deep learning networks can do much better. The point of this reservoir network is it's relatively easy to implement, and it doesn't do too badly. Okay, but that's a classical task, and ultimately we want to go into the quantum regime. So these polaritons, they can also show quantum optical properties, and here the key figure of merit is the second order correlation function, which a long time ago was predicted to drop below 1 and approach 0. So for us, 1 represents a coherent state, that's essentially classical state, and 0 represents the single polariton state or anti-bunch state, which ideally we have in each of our microcavities. Experiments were also done, and they saw the onset of this blockade, but unfortunately they only achieved G2 about 0.96. So we're still very close to being classical, although we at least have the onset of some quantumness. And I should also say that this initial physics is if you have a single cavity. And if you have multiple cavities and you couple them together, then even if you have this weak interaction, you can still have significant quantum effects. So in particular, we predicted that even if you're down here on this scale is the strength of nonlinearity compared to the dissipation rate. even if you're down here on this scale, if you have multiple cavities, you can actually have the G2 approaching 0. That was the theoretical prediction. The experimental realization, okay, it didn't quite get to 0, but it did pretty well. So it's certainly different from 1, and we no longer have to work just with coherent classical states. We can work with quantum optical states, even though we have weak nonlinearity. So given this, we came back to this scheme of the reservoir network, and we rewrote the theory using a standard quantum optical model. So this is the equation of motion for the system density matrix. We have some Hamiltonian terms that account for the nonlinearity coupling between the different cavities. We have the dissipation term in some Lindblad form. Then all of these terms just describe how the system is excited with a general state of light. Okay, so we're not just going to assume it's excited with some coherent state, which might correspond to a laser. We will consider that it can be excited with even some non-classical state of light. And we're still going to assume that we can measure the average occupation numbers, and then we'll sum them up with controlled weights to get some desired result. But then the question is, what should this thing do? So we make it quantum very well, but why is it going to help us? So here the feeling was that the classical reservoir computer, it can recognize classical patterns. So the quantum reservoir processor, it should be able to recognize quantum patterns. So what is a quantum pattern? Well, imagine we have some state of light, and we want to characterize its non-classical properties. Maybe we want to know, is it entangled or not? And so using this quantum reservoir processing geometry, we calculated what should be the success rate in recognizing entanglement. We consider a different range of states. And okay, it's not perfect, but it does pretty well. And here I should say that we considered a very small-sized physical network composed of just 4 of these coupled cavities. So it's really very small if you consider those the number of nodes. Okay, the Hilbert space much bigger, but we considered this small number of nodes to kind of inspire people to make it. Don't want to make it too complicated to realize. So even with 4 nodes, it will improve with more nodes. We get the success rate, maybe about 90% for the different classes of states. And I should stress that here we're not doing any correlation measurements. So usually in optics, to decide if something's entangled, you might need to do some interference or homodyne detection measurement, and then maybe change some phase shifter, some wave plate, measure something else, and then you combine the different measurements to say, is it entangled? Here, we don't have any of that. We don't have correlated single photon detectors or anything like that. We just measure average occupations, and we use this reservoir, we use the standard training procedure for reservoir computers to say how we should add up the occupation numbers to say, is it entangled or not? Of course, there's a cost to that. So to know how to choose those weights, you need to start with some set of example states that you know whether they're entangled or not. Okay, this is because we're using effectively the supervised learning algorithm. So we need to start with some states which will be our resource. But still, it can predict what will be the entanglement of states not in the training set. And I appreciated I appreciated all of the earlier presentations, but especially the one of Kishor. So he was showing this classification of what is classical and quantum. So I believe this is one of the simplest examples of the quantum, because we're doing a quantum task. Okay, classical system cannot determine non-classical features of a quantum state because you can't feed it into the system. And I would claim it's simple because we don't assume any quantum computer. Okay, there are certainly many more advanced schemes in that box. I think this should be one of the easier ones to fabricate initially. Okay, thumbs up, I think means we agree. Okay, so, to be fair, this prediction was quite old, so it's taking us some time to work with the collaborators to get it realized experimentally. I don't yet have anything to show there, but do I have a few more minutes?
-1.
-1. Oh, okay. Okay, sorry, I was going to say something very interesting, but I don't have time. Okay, so we also realized that this set of cavities, they can actually represent spin Hamiltonians. So things like XY Hamiltonian or Ising Hamiltonian by mapping the phase of the polaritons to the spin. Okay, and it turns out that if this system is given multiple pulses, then it will eventually settle into the lowest energy state of this spin Hamiltonian, which corresponds to the NP hard problem. So we think this might be some new potential direction to go in with these plutons. So far, we only did it with classical theory. For us, it's open question, can we find quantum speedup? Okay, thanks for giving me the extra one.
Thank you, Jim. Yes, sorry for being kind of draconian about this, but there's a lot to absorb. We have limited time, unless we all want to stay here for the rest of the day. Okay, so Liew is our next presenter. Oh, Tim, I could have given you more. Sorry, he has not that many slides. But he's going to tell us about complexity science. Take it away.
Okay, thank you. My talk will be pretty short, basically just 3 slides. Yeah. So the goal mainly to motivate the subsequent discussion on how perhaps AI can be useful for complexity science, or complex science can be useful for AI. So here itself, basically we understand that AI has been very useful for us. It has developed many computational techniques which we can use it and plot it and maybe find new results and new discoveries. But on the other hand, something like science can also go back to the computation algorithm. For example, complexity science could also go back to improve on machine learning. So for example, well, we understand that graphical neural networks use graphical data. It could be complex network type of graphical data, or reservoir computing. You also have reservoir, which is random networks, but you could have clusters, community structures within it. Maybe that allows some sort of understanding of the learning process that's underlying the machine. So the question would be, for us to know that machine learning AI can do so much, but how much we can discover from science depends on how much we can develop further the tools that goes along with it. So that is not a non-trivial problem. So I think the community is working on it, especially those people who are upfront at the frontier of computer science. They're looking at many aspects of it. The white box instead of black box thinking. So how are we going to pursue this, right? In our case, in Singapore. So that's one thing I hope this workshop here will motivate that in the next hour. So to continue on that, I will just briefly in the next 2 slides show a bit of what I've done with respect to complexity science. Maybe that could provide some sort of ideas. So I've been working a lot on transportation together with Yang, which is also here. So what we do is that transportation actually has, especially public one, there's buses, there's taxis. Of course, people have been studying this for a long time. They try to schedule it so as to optimize the time of travel, the waiting time. Sometimes you wait a long time for the public transport. So, but now there's many big data, many data coming in real time. So how can we make use of the computational resource and do it in a way that is efficient? That's not a non-trivial problem. It's an empty hard problem. It's well known to be like that. But nonetheless, well, there are clever way, smart way. So instead of saying intelligent, we say smart approach, right? Yeah, to be fair. Yeah. So in this case, we try using reinforcement learning. We try to use reinforcement learning. Reinforcement learning is a smart approach because it doesn't explore all the base space. It just experience whatever things that happen and try to optimize it in a way that could be better. So we tried it and it works well, improves. In fact, it shows emergence in some of the strategy. So we train the network, very experienced, by creating an agent-based model, which is also an idea from complex science, and train it using a Q-learning, and finally it shows there's 2 types of strategy. One is coding, which is what people have been using. But we discover a new one, which is snowboarding. Snowboarding means that the bus reach there, and find that the bus behind is very near, and you tell the people, don't go on, wait for the next one, and then go. This strategy is not used. Why? Because it's common sense. If your bus is empty and the bus driver tell you, don't come up, wait for next one, you'll be angry, right? Yeah. But the machine doesn't care. You just do it rationally. And then you found that if you really obey it, the time is be short. So we see that machine learning algorithm can discover things, but whether it is relevant or not, they don't care. So we know that there is something to learn from all this experience. So that's one thing I learned from doing this. And so those are the Q table we learned, and there's the structure of the transportation network that we have. But the key thing now is that we know that the real system actually is not constant. It is non-stationary. When we go out and take the bus, sometimes crowd will happen, right? But we know that reinforcement learning, they use Markovian kind of thing. This is a Markov process. So this is one of the weaknesses. So how can we actually make it such that it can deal with non-stationary situation? In fact, research has been doing that. They look into adaptive type of approach, how to adapt it with the system. Furthermore, there's multi-agent system. The buses are like many agents and learn from each other how to cooperate together with all the data coming in. So these are some of the challenges that relate to complex systems. So this is one aspect that one can think more on how to make use of ideas in complex systems like adaptivity, information flow, and so on and so forth. So to improve machine learning and improve complex systems. The final thing that I'm going to talk about will be another aspect, which is causal modeling. Why causal modeling is important? Because now to approach what we call interpretability and explainability in AI, one actually need to make some sort of causal inference. It's one aspect. I think that is not exhaustive in the way. So we need to know variables, which variables depend on which other variables. So here on your left, you see that there's the Earth system that many data in which maybe talking about rainfall pattern or temperature profile of the Earth. So there's a lot of data. So the idea first, of course, is dimension reduction, reduce. But next thing is that there is a need to do some sort of causal reconstruction. So which variables depend on which other variable. So that is not a straightforward approach, but there's already progress in that. People have already made use of some sort of operant inference method to deduce the link between the variable, and from there actually map back to the original system and explain why that particular hurricane could happen because of some maybe fronts that happen at the other part of the world. So these are some causal link. This is not work done by me, but the other one is something that we make use of from the spiking data from the monkey visual cortex. The monkey actually looks at two scenes. One is a random scene, and the other one is a natural scene where another monkey is wading through the water. So you can see that on the right side with the noise, we perform using a developed approach. We use what I call the Jacobian Granger causal neural network to infer the link between many of these neurons. So the one on the left, the white noise, there's many connections between the neurons. On the right, when dealing with a natural movie, we see more structure. So we see that by making sort of causal inference, there's some sort of pattern that relate between the neurons. So something can be done in that perspective, in that direction as well, to understand how information is linked between important components of the system, and from there make maybe some clever guess on what is going on in the structure. So things are still working on, and I do not have answer for that. So basically that's it I have. So hopefully this will help to inspire some sort of thoughts as we move the next piece. Thank you. That's all I have.
Thank you, Liew. Okay, coffee is ready, but I'm in your way. I have a 10-minute presentation. But if you feel compelled, you can go get coffee. The reason I would like to present this work is because it doesn't seem to be captured in other people's talks as much. Okay, here it is. I guarantee you there's a lot of mid-journey in this one. So please do spot the generative AI in here. Okay, disorder and order. Understanding disorder by learning their motifs and their hierarchies. I'll explain a little bit what that means. First, I did none of this work. Actually, a little bit. But you cannot see anything here. But these are the people that did it. My PhD students and postdocs at the top, and then a bunch of people that I acknowledge. You might remember a quote from Feynman. We do not know the rules of the game. We don't know what they are. All we are allowed to do is to watch the playing. And of course, if you watch long enough, you might eventually catch on to a few of those rules. The rules of the game are what we mean by fundamental physics. That's great, if you know what the chess pieces are. This turns out to be a big hole that we don't really know. What are these chess pieces? So this is where we mostly do our work. We do unsupervised, semi-supervised learning. Stuff that, many of the supervised work sort of builds upon. The question usually is, where are the labels? Look for Duane, right? And the problem that we face is that if we average the wrong pieces together, we get inconsistent rules. We don't have the right motifs, and we get sort of weird phenomenological motifs that appear. So I'll just show you some of the things that we have been doing. You want to think of us as data miners, I think that's quite accurate. But the tools that we have are also quite simplistic. And I think there's a lot of scope to try to push this forward, to try to find better ways of doing this. So are there simple rules to disorder? It sounds like a funny thing to do, but ask. But are two different things that are disordered the same disorder or the different disorder? Is there a vernacular to describe it? So we found that in two-dimensional systems, it's a little bit different. You could have simple motifs with complex hierarchies for composing them, complex motifs with complex hierarchies, and so on and so forth. For different systems, you can characterize it that way. So these are your different chess pieces having different rules that they come out from. And then if the rules are sufficiently entropic, we can also find generators, very efficient generators for them. And we have been trying very hard because we want to understand the different pieces. We're trying very hard to stay away from using deep networks to learn the features first. We do the correlation afterwards, but we try to handcraft the feature learning part to be as interpretable as possible. And the other thing is also about disorder, right? When nanocrystals form in solution, do they actually go through a liquid phase before the nucleation? We know that from melting point depression that small enough crystals, because of the Laplace pressure, squeeze it enough that it should go through some sort of liquid phase. But do we actually see this? And can we see this just by watching crystals of gold nucleating out of water? Do we see a liquid amorphous state appear before the final crystal appears? So these are the types of things that we do, very data-driven, looking at the data and asking these questions as we go forward. Then once we start seeing all these different variations, we can start asking the other question, which is which of these structural variations within the ensemble are explainable in the very basic sense that we can model it. If we can model it, at least we can make some predictions. Whether we can explain it very simply, that's a different problem. So here is a long sort of hypothesized version of something that you see every day. It's soot, right? It's a aerosol soot. And soot, because of the way it combusts, because of the availability of gas and the combustibles, have what people think to be some sort of self-similar structure. And this has been hypothesized since the 70s. Nice mathematical models for this. And the question is it really the case? Can we actually look at single soot particles and see the self-similarity in them? What's the way to do this? Just measure a lot. And so we have been using this technique to interrogate single particles at high throughput over and over again using X-rays with X-ray free electron lasers. I won't talk about that, but the idea is basically you can shoot something into a path of a pulse X-ray beam, like aerosols, image them one at a time, many, many of them, water droplets that are super cooled, that are nucleating, again, for a different thing, or nanocrystals. And each time you amass a very large number of observations of different nanocrystals, water droplets, or whatever you want, with some variability. And then the question is, are these variabilities meaningful or not? The one thing we do face, so I won't talk too much about the physics behind this, but the one thing we do face is the increasing data load that's coming in. And for example, back in the day when in 2009, right, we were asking the similar questions, we had maybe hundreds or thousands of these meaningful observations to look at. And then this is a log scale vertically. Then when it came to supercooled water, it started scaling up to tens of thousands, right? Or maybe hundreds of thousands at that point. And the most recent thing that we just published it's in the press, sorry, is of the order of 2 million different nanocrystals that we need to look at, right? And then the one that my graduate student is now suffering through is about 100 million. There's 100 million ice crystals. Observations, by the way, some of them would have 10 or maybe even hundreds of nanocrystals in the image itself. So you have a lot of variability. What structural variability can we understand? What can we model out of this whole thing? So I'm going to put Irvin's face. The things that we're mostly doing here are trying to do dimensionality reduction in a meaningful, interpretable way, right? Then we also try to use this sort of persistent motifs, right? Trying to find these persistent structures that are interpretable in collective motion of biological cells. So the idea is this is done by Ling, a PhD student in my group. So if I just showed you a few simulations or even actual data of cells interacting, right? You can see that they're all initialized the same way, but the dynamics are a little bit different for each one of them, right? Would you be able to tell, just by watching the movies of it, what are the coupling constants, the important coupling constants in the model that describes it? This inverse problem turns out to be extremely difficult because we want to match experimental data to models, and this is usually the missing bit, right? So this inverse matching, we don't have a good solution for, but it's very data-driven as well. And then the other question, which I like Liew slide on this Jacobian, I need to find out from you the actual term from it. This is work that was done way back, pre-COVID. We want to define whether or not there are persistent transmission routes of dengue in Singapore, right? The way to do it is just every time somebody reports dengue, right? Your blood is sampled, and then the place and the time at which you report is registered and kept in a database. Using that information, can we actually infer what are the persistent transmission routes between different points in Singapore? We started thinking about the data all the way back in 2018, but obviously this is network inference, and it's also very sparse and incomplete data. And the question is, can we actually do this? And can we find if the network is changing over time? So this is work that our NEA friends are helping us with. Will come up soon. And then I guess for the opportunity, right? I think the opportunity here for us is if we can understand these priors that we gained from understanding these structural variations, can we then improve imaging outcomes or some sort of inference outcomes, right? Can we run what we know backwards to make inference? And turns out that you kind of can, and this is done by Duane. And this is one of the things that I don't know if you're imaging, this is one of the holy grails, right? Whether or not if you have a 2D image, you can infer the 3D object from. A lot of electron microscopy and high resolution microscopy is always stuck in 2D because our detectors are mostly in 2D. If you want to measure something out of 3D, what do? Well, if you understand the variations in the object, some of them are important, some of them are not important, then can you coarse grain away the not important ones to actually take a 2D image and pop out a 3-dimensional structure? So it turns out with certain types of priors that is possible. We're still trying to generalize this overall. So yes, it's called pop-out metrology because of the popping outs. Okay, I want to thank the funders for supporting this work. And also, thank you for your attention. Okay, so we're at the point in the program where everyone's tired. We've absorbed a lot of stuff. There's questions from different speakers. There's a coffee break right now for about 20 minutes. So that means until 10:40. So please feel free to mingle and have coffee and ask questions to speakers. At 10:40, please come back And we'll have a few different clusters where, I think the clusters are quantum machine learning right now. Let's see if I remember the rest of it. There's many body physics, there's complexity and critical phenomena, there's data-driven discovery. And if during the coffee break, there's 4 right now, but there's 6 tables. If you want to propose anything else, come talk to me, we'll spawn a table for you, if you have your friends here as well. The idea is that within the hour of the breakout session, you could brainstorm, network, find out what's nice and interesting, but your table should produce one grand challenge that we can propose in a forum. So every table will have a grad student or a postdoc with the slides, and they will be the note taker, they will be the scribe for you, okay? But for now, you have an agenda to get some coffee. Please come back in 17 minutes. All right. Okay. We have been given a task. We meaning all of us. Okay. So every table will have note takers. Can the note takers identify themselves? Note takers at your table. So data-driven discovery is all over there. Yeah. Who is part of data-driven discovery? Oh, it's me. Sorry, I'm the note taker. Yeah, sorry. I will be there. I'll be the note taker, or whoever else wants to be. You can pick one. Yeah, let's pick that one. Okay, so the very beginning of the process is just brainstorming, right? People introduce your idea, you propose your grand challenge for the group, you think why it's important, people duke it out, right? And people introduce themselves within the group. 20 minutes, 30 minutes, however long you need. At the end of this process, there has to be a nucleation of a single slide at least of this format. That's where the note taker will really have to get you guys to fill this out for him, okay? So state the vision and the challenge as specifically as you can, okay? We're trying to get this into a shape which is malleable enough for the white paper eventually. So get it as close as possible to something which is believable, okay? And explain the potential. If you solve it, what is the impact, right? If you solve this grand challenge, what's the impact? As clear as you can. If you have types of AI already in mind that are not off-the-shelf AI, right? Not something that you could just pull off the shelf and just work. You know that this is a difficult problem because the size of data is high, the complexity is high, and off the shelf it's not going to work. State it here. And then I guess the last one is, why is that group of people that you're part of the right group to do this? Now, within the group, let's say you've decided that there's a natural bifurcation. Let's say two subgroups within the group think that they each have a different grand challenge, then the group bifurcates because there's 2 note takers per group, and we allow at least 1 bifurcation per group. Okay, so then you decide who the next co-lead is. Okay, so to get us going a little bit, ChatGPT has given us some grand challenges, which you probably cannot see, but it's managed to steal, I think, from other people's proposals, which is why you ask it over and over again, it keeps spitting out the same text. I think it's a very low tech, not that many people are thinking about this. Okay, there is explainable AI for physics, robust control of complex dynamical networks, AI for emergent phenomena, astrophysics, computational, quantum materials, scientific discovery, autonomous, that's what I'm interested in, complex system, blah, 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 okay. And then the issues are also here. Okay, I'll leave this slide up in case you guys want to have any inspiration. The problem though, is that ChatGPT can't write the whole thing for us because when you ask it for details, it really screws up. It gives a lot of generic stuff that's just wrong or inconsistent, okay? I don't know if I can show you, there's a lot of problems. It basically says, if you give it, okay, topological phases for condensed matter emergence, what is the challenge? What can be solved? The solution is to learn from data, and the challenge is we can't generate enough data. So there's a contradiction between the two. It basically says, I need A to give me B, I need B to give A, but I don't have A or B. So what do? I don't, it's not logical, but this is quite useful. Okay, if you can use this as a starting point. Okay, so we have about an hour. So if the snacks and all the food is still outside, feel free to walk around, feel free to mingle, but 20 minutes of just brainstorming, duking it out, and then later on, float up an idea. Okay, so after this, the leads of each group will bring forward, I will have the slides come back to me, and the leads of each group will present for you. Okay, and then the Q&A and all the questions about it and all the larger discussions will happen for that for roughly another hour. And then it's lunchtime. Okay, all right. So please proceed. We are at 12 o'clock. We need to eat by 1 o'clock or vacate by 1 o'clock. I think given the amount of very interesting conversation, I think it was a mistake to put this up because this is useless. Because I mean, obviously, I thought, oh yeah, everyone's gonna have a grand chance. No way, it's gonna be all over the place. Dario, right? This is terrible. But it was great for generating ideas. I think because within group we already have so many ideas. I think now is the point to start sharing, comparing notes, and having different groups either connect or enrich each other's ideas. Okay. So who would like to go first? The smallest group. The many body group of the smallest group. That is kind of ironic. But but the complexity group is the largest one. There's a microphone here. Okay, so if does this work? I hope it works. So people. Okay, very good.
How much time do I have?
Well, equipartition theorem, 15 minutes.
Okay.
Wait, keep it kind of shortish so that people can have.
I'll try to keep it short. We discussed for half an hour, people trying to think various different challenges and impact and ideas and so on. And then I think we converged on one single vision. We follow the homework, okay? And that is scalability. And to be more precise, we mean the ability to learn multi-scale models. So physical and the multi-scale can be both for the neural architectures that we use, but also the physical models that we want to study, and be able to go from the atomic scales to very large systems. Why do we think this is impactful? Is because it can allow deeper understanding of emerging behavior. And it can just allow you to also study much larger system and then look at their different resolutions. We go zoom in and zoom out. So that it can be very powerful to design new systems and materials and so on. And of course, they can help us to predict new properties. Now, what kind of type of AI would you need to do this? And we started by saying all of them, basically, and then also none of them, because the difficulties. One difficulty, for example, is that if you want to do multi-scale, at different scales, we get very different data. Okay, so how you bring it together in one single setup, right? For example, but in general, generative models should be pretty useful. If your complex system is actually quantum systems, then you may want to have, you may need to play with a quantum architecture. Graph neural networks and few shot networks were also mentioned. But I guess one key aspect there will be a mixture of experts. They could be able to manage these multi-skills problems. Challenges, well, sorry, no, not really the challenges. Can we use off-the-shelf machine learning models? Of course not. You need to give us money so that we can do some stuff. No, seriously speaking, not really, because they are generally tailored for unique tasks, very few tasks, and they only take different single type of data, actually, and that's not what is needed here. And then for some of the problems we're playing with, they're just not accurate enough. So there is a lot that needs to be improved. Now, the last question, why are we the right people to tackle these challenges? I didn't fully understand this sentence. So we rephrase it differently. And the way we rephrase it is, what kind of people will be able to tackle this? Okay, which may not be us, but maybe it's us. So we figure out who are these people, what are the characteristics, and then we see whether we have them here. I think we do, but okay.
ChatGPT has an answer.
Okay.
We can do that one.
Fair enough. So the people we need are people who work in different fields and in different skills, of course, because we're looking at scalability. And then, with experience in using AI in science, okay, that's quite straightforward. And then, preferably, then have the data, okay, because we want to do this kind of things. So if we, in this room, or in Singapore, in our ecosystem, we have these abilities, I think, yes, we can tackle this problem. Of course, computing power. Okay, thanks. That's it.
Okay, other groups want to chime in, add stuff to, challenge? This is the time to go. I think you looked at our notes. Why is it so similar?
You are the one walking around, not me.
Okay, who wants to go next? Quantum? Okay, Quantum goes next.
Okay.
Yep.
So, I mean, I will try to summarize, but yeah, I mean, please interrupt me, like, it's not yet. So, first thing, the vision and the challenge. So basically, the vision is to merge state-of-the-art AI and quantum information techniques to design, let's say, quantum enhanced AI with reduced resources. And the resources could be, like memory, data, let's say the time complexity, the number of samples, in general, reduced resources. That would be one. And basically, the challenge at the moment that we are facing, let's say, is that in classical case, like the amount of data that we need, let's say for generalization, of data. On top of that, let's to solve certain problems, the processing that we require can be exponentially high. And yeah, like so the time complexity is there, like the data complexity, the energy requirement that can be also very high. Actually, the classical techniques suffer at multiple fronts. You can keep on this for various resources. Then so that kind of like tells us about the potential impact of solving the challenge. Because so I was just giving this example that AI and crypto, they are quite opposite of each other. Like in crypto, you try to hide pattern. In AI or ML, you try to find pattern. So let's say every time some problem is, let's say, difficult to solve through ML, the crypto people get very happy. Okay, we cannot learn the pattern, so let's use it for security. Let's use it to like encrypt our message into ciphertext so that the adversary cannot learn. But then when we have a new fundamentally new technology, let's say quantum can break the encryption. So the crypto people get sad, but then the AI people, quantum AI people get happy because now that can help you, like learn those classically difficult to learn problems. So it's already you see based on like crypto, there can be a separation between quantum and classical. And you can rigorously prove guarantees where quantum can help you generalize with less data, can require like smaller amount of memory, can require lesser time, can like in general the complexity can be much smaller than the classical. So it will have implications, like the impact would be all these transformer technologies and so on, and they will not scale. And actually there are many problems, let's say, which are fundamentally quantum mechanical, like which was mentioned by him. Like let's say you try to like learn to code fundamentally quantum data, and for that, like normally let's say in CERN at the moment, what they do is that they measure it, get the classical information, and then process it. But what would you ideally would want is that you take your quantum data and directly process it. And there are many examples where you can have separation between quantum. Like quantumly, you will require, let's say, constant amount of data. Classically, you try to process, you will require exponential. Let's say measuring purity, for example. 2 copy swap test gives you purity. Classically, you try to measure exponentially many samples, then you process it, then you get it. So you see that it has applications, like it has impact at multiple fronts, and you can prove that rigorously. what type of AI might be able to solve the challenge? Quantum AI. Basically, and you can, like design such AI using, let's say, existing quantum algorithms. You can think about, like some of these analog devices, and you can use that, for example, with, let's say, quantum reservoir processing networks. You can think of quantum neural networks, and and many of these, like tools and techniques which are out there, and like that needs to be developed. Can this be solved by existing off-the-shelf? Classical techniques cannot solve it because you see the problem there. So you need these techniques which has to be fundamentally quantum, and there are many challenges which I think some of them I kind of discussed during my presentation, and as Dario said, to solve those challenges that are needed. And why are we the right people to tackle these challenges? So Singapore has, like Quantum Institute, like history, like long history, like there's AI Institute, Asst is the Center for Future AI Research. Then like NUS has this AI Institute here. But let's say we are here, like we are sitting, like we kind of, we have experience working in both quantum and AI, and given our past work, research papers and so on, projects that we have accomplished.
That sounds like a good proposal right there. Just convert to text.
So I think that's it. If I miss something, maybe.
Okay. I would like to spark a point on that, because you brought up this very interesting dynamic between crypto and machine learning. And to me, it feels like is the decoder and encoder structure, except they're separately trained. And the encoding is so efficient, the decoding sucks, right?
Yeah, so you can say that, yeah, like so that's why they are trying to go beyond post-quantum crypto. So so they are trying to, like, let's think of a problem which quantum cannot solve. So a quantum adversary, let's say, now looks at the ciphertext, they should not be able to learn. Yeah. So, like they will not be able to break. So that will give us security. So every time, like you operate with computationally bounded adversary, because you cannot work with information theoretic adversary. I mean, there is this theorem due to Shen, which says that for information theoretic security, the size of the key should be at least as long as size of the message, which requires too much resources. So we always, all of our public key crypto system and everything is in the computational, with computationally bounded adversaries. So far people have been thinking about, like the adversaries probabilistic polynomial time. Now they are thinking about, quantum polynomial time. And that's why like you need to go one step higher to, provide security. But then, I mean, in crypto case, people get worried with sure, but like the AI people, they will be very happy because those problems, like nature is fundamentally quantum mechanical. And if you want to learn nature, better use quantum AI.
Any other thoughts from other tables? Okay, I'm going to steal the third spot because I see the complexity people has 2 boards. So I'm going to go first because it's fast. Dario took our notes already. Just kidding. Data-driven discovery. We have something on multiple length scales also. Matching multiple length and time scales is a perennial curse of a lot of our work. That's why we have these Frankenstein models. And that's part of the reason why looks good is not good enough. Looks right is not good enough because it can look right at some length scale, but if you zoom in, it doesn't work anymore because you have Frankenstein some details in. And I think this is one of the fundamental challenges. I think if abstracted, this is how it sounds, but there's also a fundamental reason why this is difficult. Because if the problem has too many parameters and too few data to learn, the only way to make it learn is to regularize it. You have the coarse grain to make it well posed. That means you're going to a longer length scales. So those models are trained to be well posed, otherwise it's not trainable. But when you try to match it now to a full of detail, ill-posed problem again, but you can simulate for very short sequences, you're always going to have this mismatch. And this seems like a fundamental difficulty that many of us will need to solve, right? And then there's a question of discovery, which is how do we interrogate the latent space of complex models, especially things that are not feed-forward, like knowledge graphs, where it's not clear where exactly you would interrogate what the model has learned, and has it learned something that you don't know about, that is interesting, that is parameterizable, that you can use to make predictions. The latent space part is first, it's hard to find, and second, there's not a lot of tools really in that space. They're very simple dimensionality reduction type things in there, but they're based on simple geometric considerations. Okay, can I get a show of hands? Who's heard of the manifold hypothesis? Okay, not that many people, but I like to call it as well posed. The hypothesis is well posed as Kolmogorov's complexity because it's not well posed, right? The hypothesis is that there's a low, in any real data set that you can collect, there's a low dimensional manifold that embeds that in latent space that could embed all the measurements. So you only have to learn this low dimensional manifold. But the problem is we don't know if it's there for your data set or it's not. And it's always going to stay at this ill-defined hypothesis. Then there's a problem of when you actually face the data from which you want to learn from, which is huge, how do you get that match? There's always a size scale mismatch with models, the predictions that it can make versus all the messiness of data. And there has to be a dimensionality reduction, usually on this end, before you can even start matching. And this dimensionality basically is learning features that are important. But this is a chicken and egg problem. What is important? Well, it's important because you want it to be important so that when you try to match it with models, you will find mismatch. But which set of features, which combination is the one that gives you the mismatch? You won't know it until you try it. Doesn't work, you keep going back, right? So this is the chicken asking the egg for advice, and it's impossible to have a clear answer. I lied, that's the second one. Well, okay, the other one, actually they're all related. It's we talked about whether or not we can see this multi-scale appear in the latent space, right? If there's some form of multiple length scale that appears in the latent space that we can exploit to do multi-scale learning, but we can't get to it because the latent space is hard to interrogate. And then did the model learn something interesting, useful that we didn't know before? That's it. Okay, so that's data-driven discovery. You see, multi-scale. Yes.
I have a question about the manifold hypothesis, because manifold is a very specific mathematical object. So why, aside from a fancy word, why is there in this hypothesis a manifold specifically? Because we know that, okay, almost all real data exists on a small subspace of all possible data, which is very easy to imagine for images, for example. But why do we make a leap from a small subspace to specifically manifold?
If you're asking me, I didn't come up with this. I was tracing for this. Who was the first person that came up with this? Apparently, there's a Reddit post. No. This is pre-Reddit. There's a Reddit post where Joshua Bengio basically said it's a very old machine learning thing, and he pointed to some reference that I couldn't find. So people have hypothesized. So yes, indeed, the manifold has the properties that it's got to be Riemannian, that you have to have it's locally flat, you can find like differential operators and all that nice stuff. But in actual data, whether or not that exists, is still hypothesized. I'm not sure why that is. The closest I can think of is whether linearly, locally around the data, linearly, you can define some form of Taylor series expansion. If you can, and you linearize that part, then you have locally flat. So you can smoothly go from one measurement to the next by changing this derivative. And that's what you hope the manifold has. But the actual data might not have, because the actual data has all kinds of stuff that with noise that fuzzes you away from the manifold. So I don't have a good answer. If you find where the manifold hypothesis, who first proposed it, and if he's still alive, we can visit it. We can invite that person. We can invite that person for the touring thing and be like, can you please be more specific? What is the manifold hypothesis? No. Well, I don't remember who was the first person that first proposed it, and then people kept chasing it after. But it's been thought of by some people as the thing that has spawned a big part of machine learning because they think that it's a reducible problem. It's a reducible problem. It's not infinitely complex.
That this is possible.
So first, the hypothesis is not even well defined. So I think the proof is hard. Yeah. Okay.
You have volume those things, right? I don't know if it's capturing. So how can it be? Like this is with Ling Shao, the math department. So he's the expert, but I will try to paraphrase best I can. But what we talked about there, what he told us is there's a closure set of coordinates that's in the low dimensional space that captures, they're orthogonal to each other, and they capture the macroscopic, let's say in this case, the dynamic problem that captures the macroscopic dynamics of n number of coordinates. And then you have to pose it in a mathematical way. I don't know the mathematical framework, I'm not the expert here, but please read that paper and maybe that is related to this, but that seems to have the property of the manifold you're describing. I don't know if it's the same or not, but it's definitely a reduced dimensional space that captures the macroscopic behavior of a chaotic dissipative system, which is much larger in dimension.
I realize this is recorded or something, but I need to correct myself. The UMAP, right? The uniform manifold something like that. They have a manifold patching framework underneath it that motivates that manifold. So it's under the assumption that the manifold hypothesis works for your data set. This is how there is a manifold to look for. And then they do this sort of weird like manifold rescaling of one geometry to the next one to try to find it. And in Spirit, it's kind of similar to TSNE in Spirit, because TSNE also like does like local region rescaling through the perplexity parameter. But then this is apparently just more mathematically done. So maybe there are people that know this. There are definitely people that know this out there. And we should be able to do that. Okay, so complexity. What do you have?
Yeah, so maybe I first start by saying that it's very dangerous to tell people you work in complexity science. Because that can be many things. And usually when you say you do that and you work with the other experts in either transportation, biology, or neuroscience, whatever it is, they'll either take you as stepping on their foot, or they take that maybe has something to offer. So we try not to, so our problems we are working on are usually mostly not physical problems. We actually talk a lot about transportation, biology, and softness matter as well. Yeah, there's even talk about finance. So there's a lot of other things we are trying to talk about. But of course, we are physicists, mostly in the paper in physics, which we're trying to condense. So what gives us a unique perspective on working on complex systems? Of course, the problem statements are usually like, I guess we are scientists, we're just all always curious. We want to understand the complex system better. We want to optimize the complex system better, no matter what kind of complex system it is. But our anchor as physicists is the word phases. Because we recognize once I study mechanics that we know that many non-linear directions will give rise to different phases. Without understanding these diverse phases, what the uniqueness of the phases, it's hard for you to really understand the complex system operating within that phases and how they optimize. So yeah, so we initially try to say AI for physics and physics for AI, but actually I'm more inclined to unify the two if you really look at deep learning models that are being used as a complex system, which they are. So essentially still we are trying to understand complex systems, right? So our overarching goal is really trying to understand various complex systems and try to optimize them. Of course, there's one notion about the notion about emergence properties from the complex systems as well. So yeah, so I would say it's just one physics for complex systems, and phases is one thing we are curious. So I wouldn't even go to the details; it becomes too diverse, I guess. Let me see if I missed out anything. Yeah, that's mainly all. Yeah, the critical phenomenon we also mentioned, I mean, I don't know whether it's everyone agrees upon it. I guess some people agree that it's either the complex systems we observe, out there in the natural world versus social world. They are probably either around the critical point, at the critical, probably not, but maybe very near to it. But we don't know whether it's supercritical or subcritical. But if we do have the hypothesis, and that drastically narrows down how we do scientific discoveries, because we know what we do expect near the critical point, what are the statistical patterns, what are the self-similarity patterns, and a bunch of associated results from statistical mechanics. So it drastically narrows down the path we go, and maybe that's a more productive way to study complex systems, including AI. Sure, if anyone has other suggestions.
Anyone?
Okay, yeah. When I ask a question, I think complexity looks like it's hard to understand, right? Now you use like deep learning you mentioned, or is an expandable model to explain, complexity. So how to make the model or process is clear and understandable.
How?
Yeah.
I mean, how do we try to make the complex system explainable?
Yeah.
Well, I guess that's the holy grail questions in the field. So yeah, so I can say probably a reasonable approach is trying to understand what phases the complex system can possess and what phases operating in, just mentioning, then that narrows the ways we can search amongst the systems. I don't really have, only if anyone else has a better answer.
Yeah, so basically for now, for the complex systems, it's really complex in a way it's not easy for a universal way to understand or explain it. So sometimes when you talk about explainable physics, really explainable at what level. So using a neural network or machine learning is actually a very new perspective in trying to understand the physical system. So normally when you think about physical system, we write down equations or models to try to understand it. Yeah. Simple and elegant, but that doesn't really work for complex systems. So another way of trying to understand the complex system is try to understand it from a network point of view. That's one perspective. For example, complex systems are very diverse. But if you can model different complex systems with the same type of neural network, which give you a very good prediction of the dynamics of that network. So we can even use a neural network as a way of classifying different types of complex systems. And we can understand the universal features of complex systems by looking at the universal feature of a neural network that represents this complex system. In some sense, for example, we have different dynamical phases in complex systems. Maybe we can understand these dynamical phases by looking at distribution of the weights in the neural network, and different types of neural networks allows us to classify different types of complex systems or complex dynamics in the real world. So I think AI or a neural network is offering us a new perspective or new approach in trying to model a physical system instead of just simple equations. Sometimes we can't do this with simple equations, but we can still do something that is better than just experimental data. We can understand these complex systems using models of neural networks. That's one particular stuff I'm thinking.
Okay, thank you. So I understand it's not like physical understanding, but like a statistical,
Yeah, depending on how you define physical, maybe we can say these neural networks are also physical because everything physical is a model, right? Model is only an approximation, so it's never really physical. So so there's different level of physical. Yeah, statistical or maybe there are also dynamics you can think about by the evolution, the convergence of neural networks. So there's also dynamics in that. So there's time dependence in neural networks. There's statistical distribution. We can think of this as statistical mechanics of neural network. It's a way of understanding the statistical mechanics of complexes.
Okay, cool. Thank you.
Point? Is there a point there? No? Liew, you have something?
Yeah, I had something briefly to say, but I think it was covered significantly in the last point. So I thought that I didn't really need to mention it, which was precisely this notion that I think complexity science, to me, is a very important tool for understanding neural networks in general. I think we say AI for complexity, but really, I think what really excites me about
mentioned really complexity for AI, because to me, AI is allows us to use black box devices to make predictions. It doesn't really explain very much at all. It's just something you can think about it. It's just another analog simulator. And with the tools of complexity science, you may be able to, such as in phase conditions, understand the AI system itself. And I think that is what excites me the most about complexity for AI. So if you put in this side that you start thinking about it just AI for complexity, then I is very happy for a big challenge that's more on complexity science and understanding of AI.
Oh, you gotta pause, man. I think you name dropped in our that was well put. There's something that I've tried this on a few people. So there's something has been bugging me for a long time. So it's how the statistical mechanics become thermodynamics, right? We describe one or two bodies, and then we get the three bodies, and then in 3 dimensions, we can't solve the equation because it's a constraint. 4 is hard. And then the 3 body, the n body problem in general is this far. N is large, n is large, it's hard. N gets to 10 to the 23, it's easy again. Why is that? Right, so, I mean, at 10 to 23, there's a whole bunch of 10 to the 4, 10 to the 5, 10 to the 2 all happening inside. We just don't seem to want to care about it. But then, at the expense of not needing or having to care about it, then we figure out, we have some certainty at the larger length scale, right? So one of the things that, and also yesterday during lunch, right, we talked about this, it's about criticality. Whether a network is trained to be critical or it's below some phase transition. Is it possible that with some inspiration from complexity, we can decide on whether a model is decidable, is understandable or not. Because with these n-body problems, most of us just submit to the fact that we know the propagators forward is the way to go. Just do it, right? It's not solvable analytically. People could prove it in different ways. And then so the only option is complexity, like complex ways of understanding a complex problem. So you're in that range between 2 all the way to 10. And that's only because we're starting to see things more and more small, right? Smaller and smaller and more detailed. And that's why we're fighting with complexity now. But if we coarse grain our way back up, I had this slide about this, 18, I don't remember, 90 something. Nobel Prize winner, Albert Michelson. All right, he's famously been quoted to say that physics is decided at that point. That's just before the turn of the century. That all that we know is sort of known. I'm massively paraphrasing. It was actually wrongly attributed to Lord Kelvin, but then I picked up the wiki link that said that he was the guy that said it. So this is just before quantum mechanics was created. People thought that everything is done because the coarse grained to that level, and that's happening. And because now we're just opening up all kinds of places and digging deeper and digging differently in different directions. All this complexity is what we have to deal with. And so now with this new neural network, I guess now is a decidability question. Can we decide somehow whether these models are now too difficult to understand, or it's possible to understand, and we just need to find a way to do it? Does this work?
Sounds like a grand challenge.
Sounds like grand challenge, yeah. We're gonna go down another thing. This is too ambitious. How are you gonna solve this? I don't know. But we need to solve it. Yes, there are.
I can comment a bit not on the idea, but just one thing I did not hear, that since everybody is here in the room, I would encourage you to do this, and we do it for other workshops too, to think of which data sets allow you to attack these interesting challenges, and how will you beat the contemporaries and demonstrate that? What are the benchmarks in data? This is going to be a question that's going to be asked of all of them, because I know it's a diverse field, and you probably have your favorite data sets. But what proves that, to not to minimize what anybody's doing, but let's say DeepMind chooses a problem and they go after it, and when they publish it, it's better than anybody else. So what is that in your communities, which you can then say this data set has unsolved problem that nobody has solved, and so abstraction to that level would be perhaps be useful. I don't know if it's something that can be done over lunch or just continued discussion, but please do give that feedback, because that will be important for us to put in the report, stating that, when you're solving these complexity issues and unearthing how the neural network work, but you're going to demonstrate it on a problem that's well appreciated globally. It's quite an important thing to do.
Anyone has giant data sets?
You all have giant.
Yeah.
To find the ones you want to go after.
So for us in the data, one of the things that floated but didn't quite get into the talk was the fact that labeling is a very big problem. And so those data sets, however big, however small, labeling it is really complex. And getting that, without getting that labeled, none of the other models that do mostly supervised learning can have access. And so labeling is done by who? By domain experts. Right. So this is, if you can think of something that is like grand, big, challenging, full of data, like the 2D Mappedia or the materials projects, or something like that, let us know. We're happy to include that as part of the scope for possible grand challenges.
Maybe it's more for Kida. So I'll talk this quickly with Duane as well. It's about now AGI is no longer a dream to many of us nowadays, right? So that poses opportunities and challenges, but whether that's something in view of NIF to think about it, or what can we do about it? Because if we always fixated on solving existing problems at our hand, AGI will create new problems, right? I'm saying this also because I'm trying to sell complexities. because if AGI really comes about, it's critical for us to understand what the heck it's doing. I mean, if it really comes sooner than later, if it poses more risks and opportunities, it's something that maybe we need to be mindful of as well, rather than just solve the existing problems that we're aware of.
Including this perspective, what I'm not speaking right now. I'm just telling you what they are looking for. Just have every domain.
Okay. Okay, I see Dario showing the food thing. Liew, would you like to close?
Send the slide to you.
Oh, you send the slide to me. Good. Great. He has a closing slide. My gosh, this guy he is organized. Yes, it's important for the friends that are joining us this way. Well, let me take some time to say that I'm very grateful that I learned so much from you guys. I have the unenviable task of trying to write 3 pages out of all of this incredible stuff. I hope to capture as much as I can. If I miss anything and you feel very strongly you want to register the grand challenge or something that I didn't think about, that might be important. I feel like this is, I'm not sure what will happen out of this, right? But I feel like if we register our voices, like what we did back in 2019 and it failed, but we're trying it again, is to just register the fact, and we can put this in writing, that there's a growing need of certain types of problems, right? So that in the future, people will be like, hey, I know that problem. These guys have thought about it. We can talk to you, right? So this white paper, I hope to have that spirit. It's trying to be more encompassing. That's why we reached out to different groups rather than, specifically tiny little bits here and there. So if you can help us connect the dots together, I'm happy to write me an email. If we have time for coffee, we can talk about it. But thank you very much from my perspective for this wonderful learning journey. And if writing the thing, we miss any information or we need citations or something like that, then please please bear with us. We'll write you back and ask for like references or citations, but better just make it robust. Okay, let's use that. All right. The other problem, there's a grand challenge, is solve the Wi-Fi in this room. Or the Zoom thing. But this solution is okay.
Is amazing.
Summary. Okay. Okay, let me share this up.
Okay, thank you, everyone. So basically, it's a summary of
Sorry.
we have, yeah. Okay, so I just like to share something, grand challenge we are having. So AI has been wonderful, but there's one thing is that now for science, we want to make discovery. Discovery is very different. So I just happened to aware of this work, this for AI expertise, this work done by IBM Research, Samsung AI, and University of Maryland, Baltimore. So it is a system that uses axioms, a set of axioms, and then you use symbolic regression to actually make go through the scientific process. Basically, observation, hypothesis, prediction, experimentation. So that's basically what scientists do, right? Remember when Kepler observed, Tycho Brahe observed the planetary system, and from there have the data. Kepler actually basically do the fitting to get the Kepler's form. But finally, Newton's actually hypothesized, right? The Newton's law, which actually use it to derive and check, consistency check, and shows that it's generalizable to many phenomena. And of course, experimentation subsequently, the law is true because we send spacecraft everywhere, based on the law, so it works, right? So there's a process. So in fact, computer science is there is this ability to prove theorems already long time ago, automatic theorem proven. So there's reasoning ability in that system. So this group actually make use of that to incorporate the reasoning into the AI system. So that is something that's a bit lacking in current system, is basically just do the fitting. But the reasoning, the axioms that goes along with axioms is basically, it could be like many of the principles that we learn in the physics textbook. Einstein had the axioms, two axioms, right? The speed of light is the limit, right? And physical law are invariant. So based on that, two axioms actually reduce many of the effects. So basically, the idea is between axiom system with reasoning, and they have able to demonstrate Kepler's third law, Einstein relativistic time dilation, Morse theory of absorption. So this is published in Nature Comp in 2023. So we know that's how we discussed. So we know that AI is advancing very quickly. So every 2 years something could happen. So we do not know how this would happen to our subject, but the aim of this scoping is that we would like to issue a grand challenge that is very relevant to us, our community here, right? So that we will go to look for some challenge that would, in a way, you see what happens that just now when we discussed, we also discussed our biological system, transportation system. But this problem has also been proposed by many other groups, not just us, just using typical machine learning technique. So how would we need to be unique in our perspective? So that is actually the challenge in issuing this scoping. Okay, so the idea here is that I'm just trying to illustrate the possible advancement that is possible. I think here with quantum, right? Quantum is part of physics and how quantum information, quantum theory and tensor network and all this can be used for solve many body problem, physics problem. Using quantum enhanced machine learning, how you could solve some problem that is classically not possible, some problem that maybe is very challenging for trying to find a suitable drug in a normal classical way, but using quantum actually can be quicker. Yeah. So we see how science actually helps in machine learning, this quantum mechanics. But how also machine learning can go on to go for science. So that is also a challenge. So this is one example that go along that direction. So here I just illustrate some possible advance that can move forward. I mean, discussion about interpretability, explainability, I think it's important for science because we need to understand the phenomena, not just observing it. So there's also another important part is causal analysis and intervention, because that is also part of the process of explainability. So we need to know what, cause and effect, and causal analysis is important for that. Of course, there's some crazy idea of maybe some of this machine learning model can be integrated. I think we already observed that every one of you presented that ChatGPT is being used even in part of your analysis. Maybe some of this convolutional neural network and ChatGPT and all this can be linked together and to be augmented with each other to help to solve. Tensor network, quantum machine learning. I think these are all future type of approach, but there could be many more which my limited knowledge I'm not able to tell. But what are the grand challenges? Okay. So this is something I summarize. So you see things here that is actually what it was talked about just. Yeah. So I think in the beginning there's dependent on data, quality and quantity will affect accuracy. And I think I just use words from you. I think you recognize your word. And just generalization and extrapolation capability, whether the algorithm can do it, and also predictability and interpretability. There's also the problem of skills, the multi-skills that we talk about, data, compute, and the science, not just this, but the computation, the NVIDIA, right? That enable it to be possible, right? In the hardware. And also brain criticality and AI criticality. So this is the part about whether complexity can understand AI and AI can understand quantum and machine learning. So these are some of the connections that maybe could be a way to link to what we are going to write it. Yeah, so I think this is finally that my final slide. So these are some grand challenges. So you can solve this using AI, then maybe you can win $1 million because they are still unsolved, except one of the millennium problem and Hubert's problem that can we use it to solve Riemann's hypothesis. And maybe I know that LHC they use a lot of machine learning to try to make discovery, and machine learning can use in to solve many of the theoretical problems even beyond standard one. So this is just something, but that's all I to close. Thank you.
Okay. I have nothing else to say. This is great. Fantastic. We've earned a lunch. I will bug you more information for sure. There's a lot to digest. But thank you so much. And
Online, maybe.
oh yes, the people online. We've been ignoring you for like hours. I'm so sorry. Yes, whoever you are, thank you for staying around, even when we were so quiet. So much interesting stuff happening here. Yes, somebody raised his hand. Okay, well, I guess thank you. 41 of all 41 of you. I can't see you. Oh, sorry. Wait, there is a hand. Sorry. Beatrice. Wait, what's the hand mean? Is that a question? With one hand?
The webinar, will allow you to clap.
Okay, well, we have a raised hand. I'm very sorry. I don't know how to get to you. I cannot touch you over here. I'm not part of this system. I don't have access.
Shot?
Thank you. I clap with my other hand. Oh, there's a thing here.
38 people though.
Yeah.
Allowed to talk.
Allowed to talk. Okay, let's talk.
We can answer this one. When they raise their hand, yeah, so you can scroll. They can scroll.
All right, I'll interact. Grand challenge number 2.
This one.
Hi, please talk. Okay, we think you're clapping, but if not, please talk. Okay, thank you. I suppose you enjoyed it. Okay, thank you so much. And I think lunch is ready.